Hi everyone, we're going to continue talking about section 8.3. This is part 2. So we're going to talk about complex numbers again and multiplying them, and then also calculating powers of them, so raising them to the 4th or 5th degree. All right, so I'm going to just use a couple of, well, I think what I'll do first is remind us. Let's say we have two complex numbers. So one is going to be Z1, which I will write as, I'm going to do it in its polar form. So this would be written as R1, which would be the radius for this point, and we will do some examples. So first what I'm doing here is going to generate our formula. So we learned in the first part of this that we can take any complex number. So this is some a plus bi. Okay, so I'm just going to call it z for complex number, and it can be written in its polar form. So R1 is going to be that radius to the value and angle in its standard form. I'm going to look at another one, Z2, and so I'm going to have a different R value and a different angle. And today what we're going to do is we're going to multiply these guys together. Okay, so I'm generating the formula that's going to be given to you in the book, but I kind of want to do that so it kind of brings back some of those identities that we saw in chapter 7, and you can see where this comes into play, and then we will expand it to powers, and then I'll show you some examples. Okay, so let's go and multiply these guys together. So I'm going to take Z1 and I'm going to multiply it by Z2. So I'm going to do it in their complex or their polar form. So there's the cosine of theta 1 plus I sine theta 1. Okay, there's Z1. And I'm going to multiply that by R2 cosine theta 2 plus I sine theta 2. Okay, bringing my r's out front, and then I'll have these guys multiplied together. So to multiply them, I'm going to have to do some foiling. So I'm going to have the cosine times the cosine. So cosine theta 1, cosine theta 2. Remember, we really can't do anything about those because the angles are different. Here I'll have that plus I times that cosine theta 1 sine theta 2. Here I'll have that I sine theta 1 cosine theta 2, and then I'll have that plus I squared sine theta 1 sine theta 2. Now you can remember that I squared is -1. So I'm going to change this to a -1, and I'm going to take these two pieces and write them next to each other, and then out of these guys I'm going to factor an I out. So here we have that R1, R2, and I get cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2 plus I. And inside my eyes, this was my, I'm going to write my sine theta 1, this guy first. You'll see why. Cosine theta 1, sine theta 2. All right. Now if we go back to our identities piece, or identities formula sheet, and you look at this, so you have cosine, cosine, minus sine, sine. This is actually the cosine of the addition of those two angles. So I can add those two. And if you look at what's here, sine, cosine, cosine, sine, that is the sine of adding our two angles. I'll put square brackets here so it doesn't get confused. So if we wanted to multiply two complex numbers, we can multiply their R values and add those angles. Where this becomes very powerful is if you take a complex number and you raise it to a power. So let's raise it to like the third or the fifth or the eighth. So imagine doing this over and over and over and over again for the same value. So we would have an R, and we would just have thetas. So what's going to happen is we're going to get that R to the nth power, because we'd have an R times R times R, however many times we were multiplying it together. And we would have the cosine of the same angle being added over and over and over again. And we would have plus I sine of n theta. Okay, so let's do some examples so you can see why it works or how it works and all that wonderful kind of stuff. So we're going to kind of go through this kind of slowly, and let's look at, let's say we take z1 to be, and I'm just going to pick a nice number, 1 plus I, and we're going to multiply it, and we'll have z2 being, let's just go 1 minus I. I wanted things to kind of look nice for us and work decently for us. So, okay, if I was multiplying these two together, we could do it in the rectangular form. Okay, and I just want to make sure that you can see that it does work in the polar form as well. Yes, I agree. If I were multiplying these guys together, I would do it in rectangular form and just FOIL. So 1 times 1 is 1. I'd have a minus I, I'd have a plus I, and I'd get a minus I squared. These guys cancel each other out. My I squared is -1, so I get 2. That was relatively easy to do. But let's do it in polar form to show that yes, it does work. Okay, so we're going to take our z1, which was my 1 plus I, and my z2, which is 1 minus I. First thing I'm going to do is get them in their polar form. So 1 plus I is here. I chose nice ones so that it would work nicely for us. It's polar form. My R is at square root of 2. My angle is pi over 4. This is 1 minus I, so that's down here for 1, 1. So again, my R is going to be that square root of 2. My theta, this time remembering we like to go in standard form. Not that it really matters, you can do it in any form, but I like to do it in standard form so it all is nice and, I don't know. But yeah, you could have done a negative pi over 4 here if you really wanted to. So in polar form, this looks like that square root of 2 cosine of pi over 4 plus I sine pi over 4. This one would be the square root of 2 cosine 7 pi over 4 plus I sine 7 pi over 4. Now multiplying these together, so if I'm going to multiply these guys together, the rule is we multiply the r's together, so we'll take that square root of 2 times the square root of 2, and we add those angles. So we'll have the cosine of pi over 4 plus 7 pi over 4 plus I sine pi over 4 plus 7 pi over 4. Which gives me 2 cosine of 2 pi, because that's 8 pi over 4, plus I sine of 2 pi. Okay, now the cosine of 2 pi, that's all the way around to 0. Our opposite, or our adjacent side and our hypotenuse are the same. It's also where we end the cycle if you're looking at the curve. The curve starts up, comes back up. So we get that the cosine of 2 pi is 1. The sine of 2 pi, if you think of the sine curve, comes back to 0. So when I multiply this all out, I do get the number 2. So I can multiply them in rectangular form. I could multiply them in polar form. Yes, if I'm just doing 2 of them, working in rectangular form, so much easier. However, let's say I wanted to take z, which is that 1 plus I, and I want to now raise it to, and let's raise it to the 7th power. And if I were doing this in rectangular form, that means I have to FOIL this out. And I am not going to do that. 3, 4, 5, 6, and I ran out of room. 7. So I have to 1, 2, 3, 4, 5, 6, 7. I have to multiply it by itself 7 times. That's going to require us to do a lot of work. This is where the power of that polar form comes into play. So I can take that 1 plus I to the 7th power. I want to remind you that this is in its polar form, square root of 2 cosine pi over 4 plus I sine pi over 4. And if I want to raise it to the 7th power, that means I'm going to take my r, so I'm going to write the formula down here for us, cosine n theta plus I sine n theta. So I'm going to have that square root of 2 raised to the 7th. Then I'm going to multiply it by the cosine of, my n is 7, so 7 pi over 4 plus I sine 7 pi over 4. Square root of 2 to the 7th, that's going to be square root of 2, square root of 2, which is 2. So there will be 3 2's, which is 8. So that's going to give me 8 square root of 2. And then I know the cosine of 7 pi over 4. 7 pi over 4 is here. My 1 square root of 2, that's negative. So cosine is 1 over the square root of 2. Sine is going to be a negative 1 over that square root of 2. If I distribute, while those square roots of 2 cancel, I'm left with 8 minus 8i. Whoops, I lost my I. If I were to multiply all this out, I would get 8 minus 8i. It would take me a little longer to get there. Granted, a lot of times when we do this, this angle in here is possibly not one that we know. But I like to find ones that work. Our textbook also likes to find ones that work out nicely. You could check yourself. Feel free to do so. On the test, I do force you. I don't believe I go to 7 because this is just a lot of busy work. But that way you can say, oh yeah, it did work. I got the right answer. These two should turn out to be the same. All right, I will see you in the next video where we're going to learn how to divide. So I'll see you there.